All right, so let me just say hello and welcome everyone to the first week of interactive sessions for the course on computational fluid dynamics for incompressible flows. So I'm sure every one of you has registered for this course, and so in these sessions we will have them every week on Tuesdays from 6 to 8, and we shall be discussing some sample problems together, and our discussions won't be just limited to that. So any doubts that you have, you can, it's best to bring them up now. We can have an open discussion among ourselves and try to sort things out. See, the uh, watching lectures alone is not enough. We need to practice problems as well. So within that category, the assignments come. So for every week, you will get weekly assignments as well from NPTEL. You'll have to solve them. And these sessions are a supplement for both the lectures as well as the assignments. So here, I'll share some questions with you. You get to solve them. We will solve them together, and any questions that you may have from the lectures, any doubts or any parts that were not clear made in the lecture. So the lectures are one directional, right? So the course instructor speaks and the students listen. They can't ask anything. So these sessions are in order to facilitate some interaction. So as far as I can, I'll try to answer any of those queries that you have. If not, I can direct them to Professor Dalal, who is obviously the course instructor for this course, and we will get to the bottom of it every time. So hopefully it should be a useful practice, this entire thing. So let me first introduce myself. My name is Debjit, as you can see written in the slide. I am a PhD scholar at IIT Madras in the Department of Applied Mechanics, and I will be the TA for this course. So this is a 12-week course. So from starting today, every week we will meet during this time, as I said, every Tuesday from 6 to 8, and we will uh, have these sessions together. Okay. Let me first briefly outline how this will work. So I have some sample problems in my slide deck. I'll share them and I'll ask all of you. I'll invite all of you to try to solve them. Most of them will be MCQ type questions. So you'll have to figure out the options A, B, C, or D, or something like that. And then once you have figured out the solution, you can type it in the chat box, or you can unmute and answer as well. However you feel comfortable, you can use that mode. And then after that, we will try to see how to get to that solution, how to solve that problem. Okay. So without further ado, let us get started. So this is our first question for today's session, which is asking us that what is CFD used for? So this is our first week, and we have to first, you know, remind ourselves why even learn CFD or computational fluid dynamics. So if that is if that becomes clear, then we are motivated to work further and learn more about it. So this is the first question, which is trying to address what is even CFD used for? Why is it useful? Why should we learn CFD in the first place? So there are a few options given below. Option A is saying that it is used for studying fluid flow patterns. Option B is saying it's used for designing new aircrafts. Option C is saying that it could be used for developing wind turbines. Or is it option D, all of the above? So I can see people have very quickly started to reply in the chat box. That's great. Two of you, three of you have already responded. So I hope everyone participates in this. Okay. So good. Okay. Very quick responses. Many of you have said that it should be option D. So let's wait for others to answer as well. So I'll urge everyone to participate. Don't just view it like a lecture. These are not lectures, and as lectures, if you treat them, they won't be that good as well, as good as the actual lectures being uploaded by professor. So this is a two-way thing. You have to participate, actively participate, and try to solve the questions then and there. Okay, good. So we can see a very prompt response. Nice. Okay, so most of you have replied that it should be option D, that is all of the above. Let's see if it's true or not, if it's correct or not. So yeah, here's the solution, and it is indeed option D, all of the above. So let's go through each of them. Studying fluid flow patterns. So CFD basically is, so we know the equations which govern fluid flow for different scenarios. Now the thing is, it's not always possible to land on closed form analytical solutions. That's why we use CFD, that for complicated geometries, for you know non-trivial equations we can solve for those different situations. We can visualize the fluid flow patterns which actually happen. So let's say if I have some weird shape like this, and there is some flow coming from this side, what would be the fluid flow pattern around it? So using CFD we can visualize, let's say streamlines like this. Streamlines, as we know, are a good way of visualizing fluid flow, fluid flow patterns, so to say. So this is how option A is correct. Now, is visualizing enough? Not always. Through visualize, although visualization gives us a physical feel for what is actually happening, what really matters is some quantitative things. Like, let's say for this body like this, what would be the lift force on it or the drag force on it as a result of this fluid flow? That also we can calculate with the help of CFD. And this entire thing, this entire philosophy of using CFD is very heavily used in designing engineering systems. And one of the very crucial engineering systems which are designed by that way are aircrafts. So it's a very complicated process. Like an entire aircraft, you have to make the geometry, you have to simulate fluid flow for different conditions, for takeoff, for cruising above, then during landing, all that. And we can test new designs, find out flaws, and then again rectify them and again test them. So this entire cycle of designing, testing, and redesigning can be made very much simple and cheap with the help of CFD. Now, think if CFD was not there, if only we had to, build an aircraft every time, every new design, and then perform experiments on it, then figure out flaws, and then again redesign. So that entire process would be very expensive, very time taking, and ultimately, new aircrafts won't be designed at all. So CFD has been a very strong driver of modern growth, so to say. So a very specific example on that is the designing of new aircrafts. And following that same philosophy, wind turbines, which is, you know, recently there has been a very strong focus on renewable sources of energy. And windmills or wind turbines are definitely one strong contender there. So, designing of them or development of these systems are also possible through CFD. So to sum it up, there are these are very few specific examples. There are multiple, numerous such real engineering problems or even science problems where CFD comes into play and plays a very significant role. So learning CFD for us is a value addition to us because it ensures that we can pursue a career in multiple such areas, right? So as far as this question is concerned, all of the above would be true. All right. So if anyone has any questions or doubts, this is the time for you to ask. So I'll pause for a few seconds and invite questions from all of you. So if there are no questions, this was a very simple one to begin with. I'm sure we won't have much questions, so we will quickly move on to the next problem, which is question number 2. So question number 2 is asking us what is the main difference between CFD and experimental fluid mechanics? That is creating experimental setup and performing experiments to derive fluid mechanic insights of different problems. So option A is saying that CFD is simulation based while experimental fluid mechanics is physical equipment based. That is option A. Option B is telling that CFD is faster while experimental fluid mechanics is more accurate. Option C is telling us that CFD is more expensive while experimental fluid mechanics is cheaper. Option D is telling us that CFD is more reliable whereas experiments are less reliable. So read all these statements carefully and you have to pick out the correct one. So only one of them are true, others are false. So you have to pick one which is actually true. So you have to read the statements very carefully. There could be some hidden tricks as well within the sentences. And once you have figured out the solution, you can type it in the chat box or you can unmute and answer as well, however you feel comfortable. Okay, so once again, we are getting very quick responses here in the chat box. Okay, so there are almost 17 of us, if not more. And already many of you have responded. Good. Love to see this enthusiasm from your side. Good. So we have a divided crowd here. Last time everyone unanimously. So everyone agreed that it should be option D for the first question. And for this one, we have a bit of a divided crowd. Most of you are telling it should be option A, whereas we have a few people saying that it should be option B as well. So let's see. Would it be option A or option B? All right, so we have stopped getting any newer responses. So we will quickly go and take a look at the correct answer. Okay, so here, although it is saying that option B should be correct, actually it is option A that is correct. So it's a mistake on my part. Sorry. So the thing is, why let me go through each of these sentences and then we can decide. So CFD being simulation, this word basically means prediction. So CFD is actually prediction based, while whereas experimental fluid mechanics is physical equipment based. So we test reality in experiments, whereas CFD is just solving some equations and assuming that they should be correct. So actually option A is correct. Now, option B, although I've marked it as green here, it was a mistake on my part. It is telling that CFD is faster while experimental fluid mechanics is more accurate. Now, this second part, this is correct. Experiments are indeed more correct because experiments are reality. Whatever you see, that is true. Seeing is believing, as we say. Now, CFD is faster. This thing might not always be true, right? Sometimes experiments are way quicker than performing CFD. CFD sometimes may take months to happen. Now, of course, with the technological advancements and bigger computers that we have, uh, we can definitely say that the speed of CFD is getting faster day by day. But although it's not entirely true that always CFD will be faster, sometimes there can be exceptions where experiments are indeed more quicker than CFD. So option B won't be correct. Then going through the other options, CFD is more expensive whereas experiments are cheaper. This is in general not true because experiments take more physical equipment which are costly to set up in the first place. Then carrying them out requires a lot of effort, and there is a lot of consumables uh, involved, which can also drive the expenses up. So, on the other hand, with very cheap and very fast computational capacities available at our hands, CFD has definitely become less expensive over time. And as far as the last statement is concerned, experiments are more reliable than CFD because CFD involves you to make a lot of assumptions and uh, assume models for real physical systems and make predictions based on that, and that is always not so reliable, not as reliable as experiments. Experiments are always uh, more reliable than CFD. So anyone who has had some exposure to industry or academic CFD, you will know that once you're trying to propose a new scheme or propose a new model using CFD, you have to first validate it using experimental data. So this validation part is done with experiments since experiments are more reliable. Now, what happens is you use CFD to replicate some experiment and show that both are giving similar results, and that's how someone else who is looking at your work becomes confident that okay, your CFD model is correct, it's reliable. Then whatever other results that you generate using that CFD case or CFD tool, for which experiments are not available, then other people can say with confidence that okay, this is correct, I believe you, I believe your results. So here's the thing, so that's why option D is also incorrect. So B, C, D would be wrong and option A would be the correct one. Okay, and I'm sorry for this mistake on my part. This option A should have been marked in green instead of option B. Any questions or any doubts?
Yes, sir. Actually, I have a question.
Yeah, please go ahead.
So, in the lecture notes given in the website,
Hmm.
it has stated that real experiments are expensive, slow, and sequential. At the same time, CFD is cheaper, faster, and parallel.
Yeah.
So, if it's faster, it's correct, right? Like,
No, not always. That's the thing.
okay,
So let's say I'll give you an example. Let's say you want to there is a sphere like this. Let's say a cricket ball maybe. So you want to know that if a flow comes with, let's say, Reynolds number 1000. Sorry, sorry, excuse me. Uh, so let's say you want to know that if Reynolds number 1000 flow goes over this ball, what would be the drag force on this? So 1000 or higher Reynolds number means that this becomes a turbulent flow. Now, performing direct numerical simulations of turbulent flow would be a hugely time taking process. Instead, if you can simply set up a wind turbine experiment and perform this experiment, it would take hardly a few minutes, if not minutes, then a few hours, if you have a experimental setup at your disposal. Whereas CFD, performing CFD on that would take at least a couple of weeks, even with supercomputers. So that's why CFD in general may be faster, but not always.
okay, sir. Thank
There
you.
are very real exceptions which we can see every day. So
Okay,
this problem which I cited just now, This is actually a problem one of my lab mates is working on. So and he's doing both numerical simulations as well as experiments. So I can tell from his experience that performing experiments are much quicker than getting the CFD results.
Okay, sir.
Yeah. So that is in general true, but not always. Anyway, any other questions, anyone? Yeah, Shalini, are you trying to say something? Your voice is not so clear.
Sorry, sir. Sorry, sir.
Oh, no, no need to say sorry. It's okay. Fine. Anyone else? Any questions? Okay, so someone is telling in the chat box. We'll read that. So, good evening, sir. We learned three methods to classify first order PDE. I am confused in choosing an apt method for the assignment questions. Can you please clarify me on this? So, okay, we will go through this. I think I have some question on classifying PDEs. So, we will go through them. And if things does not become clear, we can revisit this. Okay. And we can take a look at the actual assignment questions as well after the submission date. So let's say for the first week, I think the submission date is on 7th February, right? So we can, so maybe on the next day when we meet, we can go back and take a look at the actual assignments and then discuss. Okay. So we will go through the method if there is a question as far as I can remember. All right. So let's move over to question number 3 now, which is asking us that what are the three main steps involved in solving a CFD problem? Option A is telling that the steps should be pre-processing, solving, and post-processing. Option B is modeling, simulation, and visualization. Option C is data collection, analysis, and reporting. Option D is design, manufacture, and testing. So this is like general practice. What do you do when you are solving a CFD problem? Okay, once again we have a very enthusiastic crowd telling us that the answer should be option A. Let's wait for a couple more minutes and see if others also respond. So I'll urge everyone to send in your responses in the chat box. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Good. Good. So the question number 3 of today's session is, what are the three main steps involved in solving a CFD problem? Is it option A, pre-processing, then solving, then post-processing? Option B, is it modeling, then simulation, then visualization? Or is it option C, data collection, analysis and reporting? Or is it option D, design, manufacture and testing? Okay, so most of you are telling that it should be option A. It is this one, pre-processing, solving, and post-processing. Let's have a look at the correct solution. And indeed, everyone is correct. It is pre-processing, solving, and post-processing. So these are the three main steps. So let's go through what each of them are. So pre-processing, solving, and post-processing. What is usually done, the common practice in this field? So pre-processing means you need to make the geometry, right? So usually we use CAD software for making these. Uh, then after you have made the geometry, so let's say it's a pipe flow like this, you need to specify the diameter of the pipe as well as the length of this. So that is the first step, creation of the geometry. Then once that's done, we need to discretize this into small control volumes or discrete points depending on whatever method we're using. So this process is called meshing. So you need to create a mesh out of the geometry. Then after that, you need to fix all the solver settings, right? So this involves choice of model. So let's do this else. Okay. The model can be either laminar or turbulent. Your process of calculation would differ based on that. It could be steady or unsteady, right? You could, along with fluid flow, you can solve for energy as well. So heat energy. So then heat transfer equations also get solved or not. You have to fix it here. Then in case of let's say combusting flows, there you need chemical reactions as well. All that. It could be a single phase flow, like either only gas or only liquid is flowing, or it could be multi-phase flow as well. Those kinds of things are also done. So setting up all that falls under pre-processing. Then comes solving. So in solving, you actually go ahead and perform the calculations based on the model which you have selected on the geometry using the mesh, right? So that part is solving. Then after you have the solution, solving gives you the solution. Uh, then comes either you can only visualize and be done with it, but that's not always the case. You need to derive some, uh, you know, uh, computations or quantities from these computations, which are actually important. So let's say, uh, in case of a fluid flow, we can ask questions like, what is the shear stress on the wall? We can ask questions like, what is the pressure drop required for a certain flow rate to go through a pipe or any conduit or any flow network, right? Things like this. And all that falls under post processing, which is things you do after you get the solution. So this is the overall workflow when we are dealing with the CFD problem. There are of course variations to it, but the main structure is the same, right? Any questions, anyone? No? Okay. So we will keep rolling, assuming that everything is clear. We'll move over to question number 4, which is asking us that which is not a way to discretize partial differential equations on CFD. So is it option A, finite volume method, option B, finite element method, option C, finite mass method, or is it option D, finite difference method? And once again, our enthusiastic crowd shows up and gives very quick responses. Good, nice, very nice. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 people have responded. Very good. So I'll urge others to respond as well. I can see 24 participants, maybe 2 of them are my devices. So I guess 22 of you are here. So I'm expecting 22 responses here. Okay, good. So read the question carefully first, and then once you have figured out the solution, just type it in the chat box. So there are four methods given below. Which of those is not a way? Is not a way to discretize partial differential equations in CFD? Is it finite volume method? Is it finite element method? Is it finite mass method? Or is it the finite difference method? Alright, so the entirety of the crowd has responded in favor of option C, that is finite mass method. Let's have a look if that's correct or not. And it is indeed correct. Very good. So finite mass method is not a way to discretize a partial differential equation. Now let's go through them one by one. Finite difference method is basically, if you have a domain like this, you take discrete points. So for now, my domain is this straight line, a 1D line. In this case, you let's say if this is x, and in x I have indices like I minus 1 before it, and I plus 1 after it. And at every point I have the value of some function, that is x, which is that is f, which is at x minus delta x, f at delta x, sorry, no. uh, so at the ith point it is f of x, at the I minus 1th point it is x minus delta x, and at I plus 1th point this is f of x plus delta x. And the difference between each of those points is delta x. And now if I use this template to discretize my partial differential equation, whatever partial differential equation we will have in f and x in this case. So it could be something like dou 2f dou x square plus, I don't know, f equal to 0 maybe. It's a random equation. Anyway, so we can discretize this using a finite difference method if we use a template like this. Another way, which is more commonly used in CFD, that is the finite volume method, in which case we, let's say if there is a big, rectangular domain like this, we will break it up into smaller rectangles, and each rectangle we can represent like this. So I won't draw a cube, I'll just draw a 2D rectangle. And in this we have, u coming in from one side, u going out from the other, v in from another side, v out from the other, right? And we will solve finite volume, uh, we will use finite volume to discretize the whatever governing equations we have for this small rectangle, and we will repeat that for all the rectangles in this entire computational domain, so to say. And aggregate effect of that should be that we will get a solution for the entire domain. That is finite volume method. Similarly, finite element method is also another way of doing things. Finite mass method is something that is not, not used to discretize PDEs in CFD. Okay. Any questions? I hope things are clear, right? It was a simple one. Okay, so if things are clear, we will. Okay, I have a question in the chat box. Will we have just MCQ questions for final exam, or we will have subjective questions as well? This I'm not sure. Like the exam part is handled by other members of NPTEL. I really don't have an idea here. So you can ask this in the forum. Someone will be able to clarify. Okay. I'm sorry, I don't have the answer to your question. Among these methods, are there any specific aspects which suit for any particular scenarios kind of things? Yeah. So the thing is, finite difference method works really well when you have regular geometries. One, the moment you go into irregular geometries, then finite volume method becomes more suitable for that. So the example which I can think of is, let's say, instead of a straight pipe, if I had a bent pipe like this. Okay, so then so if I had a straight pipe like this, then using finite difference method would actually be very simple. I'll simply break up it into points like this, which are regularly spaced. This is delta x, I know, delta y, I know, and it goes in I and j. So each point can be ij, ij plus 1, I minus 1, j plus 1, like that. You get it, right? So for regular geometry, finite difference method works well. But once you try to discretize, an irregular geometry into finite difference method, things become complicated as hell. So then finite volume method works better. So let's say for this one, so I'm zooming this out. So I'll use a different color of pen maybe. Yeah. So let's say this is what I'm trying to model. So it's a bent cylinder like this. So let's say if this was I comma j, this was I plus 1 comma j, I plus 1, j plus 1, and I j plus 1, right? So the difference between this point and this point is not just delta x, there is a difference in the y direction as well, right? Similarly, that's true for all the other points. They are not regularly spaced. So that's why employing finite difference method here is difficult. But instead, so whatever control, so you take this entire control volume instead of individual points, then whatever flow goes in, the same flow goes out, and so on. So similarly, other conservation equations can also be employed on these four faces, so to say, right? So then finite volume method becomes a more suitable method for this scenario. So that's why in actual practice you will see that finite volume method is the most common method which is used in CFD. Finite difference method, on the other hand, is simple to understand, and for learning purposes it is used. So someone who is getting introduced to CFD for the first time, they can write out simple codes on their own to see how things work, and for that finite difference method works really well because things are pretty simple. And on an application perspective, finite difference method works very well with regular geometries, not with irregular ones. I hope that answers your question. Yeah, exactly. This is just one aspect. I'm sure there are other aspects of it. Uh, uh, Overall, finite volume method seems to be the better one. The formulation is more difficult, but the solution becomes more accurate and easier with finite volume method. it helps us tackle the complex geometries as well. Yeah. Okay. So any other questions? Okay. So if not, we will move along. We'll move along to question number 5, which is asking us that which of these is not a regular structured grid? Option A, Cartesian. Option B, cylindrical. Option C, spherical. Or option D, triangular. So there are different grid structures, right? I'll try to simply draw a few of them. So Cartesian is this, where I have a rectangular grid. In X and Y, we can add the third dimension and make it 3D as well. Option B, cylindrical. So in cylindrical coordinates, we have something like this. So the three dimensions here now are, the axial dimension, which can be Z, the radial direction, which is R, and the azimuthal direction, that is theta. And in this case, you can discretize this as such. So I'll try to draw a simple figure. Uh, I'm not making this more ugly than I already have. I hope you can understand what the thing is. Yeah. And option C is spherical. So let's say I have a sphere like this, and this is one of the poles of the sphere. So it would be, we will have latitudes like this. Sorry, longitudes like the ones I earlier drew, and latitudes like this. Okay. So here the three dimensions are R, then the azimuthal direction, which is phi, and this one, which is theta. So the latitude, that is theta. So r theta phi coordinate system, as it's mostly called. His azimuthal direction is phi, is which longitude we lie on. And option D, triangular, is something like this. So let's say I'm using a rectangle only to begin with. But it is broken up into triangles like this. So which of these is not a regular structured grid? All of them are structured nonetheless. Which of these are not regular? That is the question. Is it option A, Cartesian, option B, cylindrical, option C, spherical, or option D, triangular? We do have a lot of responses here. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All in favor of option D, that is triangular. Okay, good. So think about it. Try to respond. Those who have not responded yet, then in a minute or so, we will have a look at the correct solution. So let me ask you another follow-up question first. What do you mean by regular structured grid? What does the word regular signify here?
So without any complex shapes, simple shapes of using.
Yeah, simple shapes. So here all of them are simple shapes, but regular has a very particular meaning in the context of this structured grids. So what I mean to say is that instead of an uniform delta x delta y, I could choose a Cartesian grid which is like very small near the edges and grows bigger with distance, right? So I'm using very fine grid structures here and very large blocks somewhere else. That is also a regular structured grid. What makes it regular?
So the similarity and the PEL.
Right. So there are two important things here. One is similarity, and another thing is the mathematical way of representing things. So uh, this is actually not regular. This is irregular. This is structured but irregular because qualitatively we can say that it is similarity, like this grid point which is very small and this grid point which is very large, they are not similar. So they are not same, they are similar but not same. Their sizes are different. But uh, another thing is that in case of this regular structured grid, which is a Cartesian grid. For example, we can take a Cartesian grid with uniform delta x and delta y. So this is regular structured. So in this case, if I tell you that what is the location of the uh, grid point, which is uh, 5 steps towards the x direction and 6 steps towards the y direction, what is the location of that? You can simply say that if you know the location of the origin, which may be here, you can say that its location would be at 5 delta x plus, or in a vector way of saying 5 delta x comma 6 delta y. This would be the location of it. But in case of this one, if I ask you the same question, uh, simply telling, you can't arrive at a mathematical form so simple as this, because as you move towards a direction, the distances covered would be different for every single grid. So that's why it is irregular. And as far as these four options are considered, it is the triangular grid which is not a regular structured grid. Because yeah, so someone pointed out in the chat box that intervals are regular. Exactly. So this, in the case of triangles, you cannot use a mathematical structure like what you can use for regular structured grids to pinpoint locations or distances, right? So that's why the correct option should be triangular, and it is indeed so. Any questions? So in the chat box, someone has asked, sir, please tell us about the local refinement. Yeah. So local refinement is used to, the main reason is to capture gradients basically. So let's say you have a boundary layer flow like this, that there is a flat plate and there is a uniform flow coming in, and there is a boundary layer forming as a result of the no slip boundary condition at the wall. So the flow profile would be something like this, right? So I hope everyone is familiar with boundary layers. In any fluid dynamics course, it should be covered. And you need to have a good background in fluid mechanics before going into computational fluid mechanics. So brushing up on that is important. If you feel the need, please do so. Anyway, we will get back here. So you can see that in this profile, in this entire distance, so let's say this is from y equal to 0 at the wall to, let's say, y equal to some L at the top, and the boundary layer thickness, we will call it delta. Now the thing is, as in between 0 and delta, there are huge, or some velocity gradients over there. So the velocity changes over here. And above delta, there are no more gradients involved. So this is basically a uniform flow from here, from this point to this point. So if you are trying to model this using CFD, so you need to create a domain above this wall, and the boundary layers are usually very thin. So going from y equal to 0 to y equal to L, if you take uniformly spaced grid points here, so you will miss out a lot of the detail that is happening in the boundary layer, which is at a very thin region, and uh, for the rest of the flow where it is uniform, it doesn't really matter. So what we do is we refine the mesh in our regions of interest where there are more gradients involved. So this comes from physical insight. Beforehand, it's difficult to say so. So, okay, there is a strategy when we can't say beforehand as well. I'll point you to that. So, anyway, so first of all, if you know that there are going to be gradients near this wall, what you do is you take very fine mesh in this region. And then as you go away from that high gradient region, you can use a bigger mesh size and keep your computational cost to a minimum. But this local refinement is required to capture those gradients. Now here comes another thing, that for this simple case, you know that there will be a boundary layer forming near the wall and there will be gradients in that boundary layer. So I refine that region. Now, if you're trying to model an entirely unknown system where you don't know where high gradients would be, what would you do then? So in that case, there is something called adaptive meshing. So what happens here is we first solve for getting an intermediate solution. Then from that solution, we can find out where the gradients are high. So high gradient regions we can identify. Then we go ahead and refine those regions and then recalculate. And we do this iteratively. So in this way, we can get a very, uh, accurate picture of whatever is going on. So let's say I have, an aerofoil section like this, and I'm starting with a uniform grid like this. Now, after solving it for a few cases, I'm seeing that this region here is actually a high gradient region. So what I do, and I go ahead and break these cylinders or break these rectangles into even smaller rectangles. Basically, it is called refining. So I refine the mesh wherever the gradients are high, and I don't touch the regions where gradients are low. I keep them big. So this could be refined here as well. So anyway, so by doing this, I can refine the high gradient region, and this can be done automatically. Like this can be automated within the code or whatever CFD software, and that takes care of it. So this is known as adaptive meshing for local refinement. Uh, So a very good question we have in the chat box, that is saying that would this adaptive meshing take a toll on the computing time? Yes. So this is one of the drawbacks of this, that first of all, with refining, you are driving the computational time up. You have a bigger mesh with bigger, larger number of nodes and elements that you have to solve for. So that is increasing the number of calculations you need to do at every single step. So that is increasing the computational time. And the second thing is, if you are doing this iteratively, usually it's not done at every time step. Usually it is done at, let's say, 10 or 50 time steps later, that the mesh is changed. So meshing itself is a highly, you know, effort taking process. So that also drives the computational time up. But these are the drawbacks. The advantage is that you get a better result, which you would have got without local refinement through adaptive meshing. Right? I hope that answers the question. Anything else? Anyone? Okay, good. So we will now keep rolling. We will move over to question number 6 of today's session, which is asking us that select the correct form of the general transport equation. So there is a general transport equation which basically is a model equation where,
Sir,
yeah,
uh, sorry to interrupt you.
no
So,
problem, go ahead.
explain again this mesh refinement and adaptive meshing. Both are same thing or different?
No, no, both are different. So local refinement means that you are refining the mesh at any particular location only, which is why local and not global. That
Okay,
is
and
that is
adaptive
the
meshing?
Yeah, and adaptive meshing is basically you are automating this meshing process. So one of the ways in which local refinement can be done is adaptive meshing. So a few time steps uh, later, you are refining the mesh. So that is one way of adaptive meshing. There are other ways as well. So let's say in situations where the geometry is not constant, let's say the geometry is changing with time. In that case, also you have to remesh every time, right? So that is also another thing which comes under adaptive meshing.
Sir, my query means in the local refinement, we used to refine the image. Means we are aware that during this season we have to
Yeah,
refine like near the wall or near the when flow geometry is changing. But this adaptive meshing, it is taking automatically. Means this is a features of that code,
yeah.
the software.
Yeah. So local refinement you can always do manually. Like you are the one who are intervening, choosing which locations to refine. So that is one way of doing things. Another is you make it automatic. So many commercial codes like Fluent or something like that, even OpenFOAM, I guess, if you give some parameters to it, based on that it has some underlying code inside it which takes care of this local refinement, and that is like automatically done, and that comes under adaptive meshing.
Okay, thank you, sir.
And adaptive meshing itself, as I told, that local refinement is not the only thing that you can do with adaptive meshing. You can do a lot more other things. One example of that is the geometry change. So let's say you know let's say I'm trying to model a wing, the wing of a bird. So I take a rectangular domain like this. I hope you can see my video, right? So let's say my hand is that wing, and I have some mesh surrounding it. And with time, this wing is flapping. So every time I have to compute this new location of the wing, and based on that new location, I have to change the geometry around it, and that would require a new mesh as well. So that also comes under adaptive meshing. Or let's say if some elastic body was used, like in response to the fluid forces, that thing is changing its shape. In that case, also you need a new mesh every time. So that also comes under adaptive meshing. So there are multiple things. Local refinement is just one of them. Okay.
Okay, sir.
Okay. Thanks. So we will move on, and please don't hesitate to interrupt me and ask questions. Please go ahead. Like that is the main point of holding these sessions. Okay. All right. So now we have come down to question number 6 of today's session, which is asking us to select the correct form of the general transport equation, which is, as I said, a template model for different equations. So Here phi is the variable. Phi can take any shape or form. If you change phi with any other physical quantity, like let's say mass, velocity, momentum, angular momentum, species concentration, anything like that, or temperature, energy, it will form a different transport equation corresponding to that physical quantity. Now, this general form you have to select from the four really nasty looking differential equations which I have compiled here. So basically there are four terms: dou dou t of rho into phi plus the this is not a gradient, what is it called, the divergence of rho u phi equal to the divergence of some gamma into again the divergence or the grad of phi and s phi, which is the source term. So if these terms are constant in all the four equations, it's only the plus and minus signs which are jumbled across. So you have to choose the correct combination from these four options. Let's look at the chat box. We have some very quick responses. Yeah, someone has reminded divergence to me. Thank you. It, all right, so majority of us think it should be option A, and a few of us think it should be option D as well. So let's look for some more responses, then we will go ahead and look at the correct solution. All right, so let's have a look at the solution. It is indeed option A, as the majority had selected. Sorry, what is happening? Yeah, so it is option A. Now let's go through these terms together. This is the correct order, by the way, of the plus and minus signs. So dou dou t of rho phi, this is known as the, this has multiple names. It can be called the temporal term or the unsteady term, and another name of it is the storage term. So dou dou t of rho phi. So basically what it's telling is in our control volume, there is rho phi amount of the quantity in it. So why rho phi? Because phi is an intensive property. So multiplying it with the density rho, which is the density, gives us the extensive property of whatever that corresponding physical quantity is within some control volume. Now, this changing as a function of time is captured by this term, which is why it's also called the storage term. So, as if rho phi is stored in that control volume, and how it is changing depends on the time derivative of it. Right? So, if this is positive, that means this is going up. If it's negative, that means it's coming down. Now, uh, this is the main thing that we are computing. Now there are different ways in which rho phi can change in this control volume. The one way it can change is that it can either flow in or flow out of this control volume, right? Along with the velocity field surrounding it, or the velocity fluxes, so to say. So the flux is basically rho u into phi, and if we take the divergence of it, that gives us the change with respect to time. So this is known as the convective term, or it is known as the advective term. So this basically accounts for all the fluxes going in and out. So this can cause a change on this term. This is one way. Another way is that even in the absence of flow, if there are concentration gradients, there can be diffusion, right? Like in Fickian diffusion, we have learned for you know any species concentration. Similarly, heat can also diffuse out, which happens in conduction. So if there is a temperature gradient, heat will diffuse out from a high temperature region to a lower temperature region, even in the absence of flow, and that is basically uh, captured by this term, which is known as the diffusion term. This gamma is the diffusion coefficient. This will also change from quantity to quantity. So for let's say if it's temperature, then this would be alpha, which is the thermal diffusivity. If it's momentum that we're worried about, then it would be the uh, uh, what is this kinematic viscosity, that is also known as the momentum diffusivity. So momentum can also diffuse, right? So so on and so forth. And the third term is like, even if there is no flow, there is no diffusion, nothing happening, then also the quantity stored within the control volume can change. That is, if there is any source or sink within it. So let's say if there is some chemical reaction happening that will release some heat, even if heat is not flowing or diffusing out from that control volume. So there is a heat source in that case, right? Similarly, there can be sinks as well, and those kind of phenomena is captured by this source term, which is either a source or a sink. Now, what would be a source or a sink? That depends on the physics of the problem and would, you know, vary from case to case. So these are broadly the four ways in which any transport equation can be quantified, and that is correctly quantified in the form shown in option A, where the storage term and the convective term are added, and that should be equal to the sum of the diffusive term and the S phi term. So basically what happens is, so if we term these, let's say 1, 2, 3 and 4, the diffusion term is actually the negative of this. So the diffusion would happen towards the negative gradient, right? So basically the original form of the equation can be written as 1 plus 2 minus 3 equal to 4, right? Now, in order to make this look more elegant, we send this 3 to the right hand side and say that it is instead 1 plus 2 equal to 3 plus 4. But anyway, both are correct. It doesn't matter. Right? Any questions regarding this? If not, we will move on. We'll move on to question number 7 of today's session, which is asking us what are the very high and very low Reynolds number approximations of the Navier-Stokes equations. So I'll write down the Navier-Stokes equations for you. So I'm writing this in one dimension only, that is x. Okay, once again, and okay, so what I am asking here is that what are the very high and very low Reynolds number approximations of the Navier-Stokes equations? So basically, if we non-dimensionalize this, so star dot E star, this is the non-dimensional form of the Navier-Stokes equations. So the question is, what are the very high and very low Reynolds number approximations of this, of the Navier-Stokes equation? Is it known as option A, Burger's equation and Bernoulli's equation? Option B, Euler's equation and Stokes equation? Option C, Laplace equation and Burger's equation? Option D, Stokes equation and Euler's equation. Okay, once again we have a very quick response, and most of the crowd is in favor of option B, that is Euler's equation and Stokes equation. Sorry. Okay, so let's have a look at the solution. Solution is indeed option B, as the majority pointed out. It is the very high approximation should be the, so I'll write down the equation once again. So this time I'm not writing the star, but you have to assume that u and x are both non-dimensional quantities right now. Okay, so I'll write this one. These are both non-dimensional. Now, for the first case, that is very high Reynolds number case, what happens is uh, this, so 1 by Re is multiplied to the diffusion term over here. And if Reynolds number is very high, you can imagine that 1 by Reynolds number would be very small. And this quantity we can ignore then. Then it simply becomes dou u dou t plus u dou u dou x is equal to 0. So this is basically an inviscid flow. So there is no viscosity here. And this form of equation is known as the Euler's equation, because if you remember, Euler was the first person to find out the governing equation for inviscid fluid flow, right? And upon integrating it, we get the Bernoulli's equation. So the very high Reynolds number approximation is Euler's equation, and the other case, that is Reynolds number is very low in that case. So what happens is so wait a second. So in that case, this inertial term u dou u dou x can be ignored, because and this is a nonlinear term as well. So Reynolds number being very low means that the inertial forces, that is rho u squared, is actually very low as compared to the viscous forces. So that's why you can simply, okay, sorry. So in that case you can modify this, so in that case you can modify this equation into, let's say you can write Re multiplied by dou u dou t plus u dou u dou x equal to dou to u dou x squared. And since RE is low, this entire thing you can ignore, and your equation simply becomes the second derivative of u being equal to 0. Now this is for 1D. In 2D, this would become dou to u dou x square plus dou to u dou y square equal to 0, and similarly dou to v dou x square plus dou to v dou y square equal to 0. This formulation is known as the Stokes equation, where the inertial terms are ignored. So this is basically like a fluid statics problem. There is a u, but any change or any disturbance if you make, it will automatically adjust. So this approximation is known as the Stokes equation. So to answer the question, option B would be the correct one. Any questions on this? So to give a better idea, like why even should we uh, pay attention to these approximations, right? So what happens is in practicality you will find situations where the Reynolds number is very high or very low, extremely high, extremely low. In that case, you don't need to solve the full Navier-Stokes equations, which is anyway very hard to do, the Navier-Stokes. So you have all the terms involved here. Solving for that may not be useful. So instead, these approximations which you can make, either Euler's or Stokes approximations. Sorry, not. So either Euler's equation or Stokes equation, if you can approximate and get rid of some terms, that greatly simplifies your problem. You even if you're performing CFD, that becomes a much cheaper, much quicker CFD problem to tackle with, right? And that is one thing. And on top of that, you will see the nature of the partial differential equation changes, especially for this Stokes equations. If you look at these are elliptic equations, right? And elliptic equations has some properties of their own which can be exploited to find the solutions even more simply, because these are just Laplace equations in u and v, right? So that is another thing why these approximations you have to keep in mind when you are first trying to model a problem. So it is always good practice to write down the governing equations, analyze each term intelligently, and smartly get rid of stuff which are not important. And non-dimensional analysis is an absolutely crucial tool which can help you over here. So instead of looking at the different numbers, whether velocity is large or density is low or viscosity is large, instead of that, you club them together into a Reynolds number and then only look at that. That is the only parameter you will look at. And that would, explain the physics to you in a much better way. You can get a feel for the actual problem, right? So I hope I can make my point clear. Any questions on this or anything else up to here? If not, we will keep rolling. We will move on to question number 8 of today's session. Now this is a different type of question, a match the following question. So we have four options on a left hand column, A, B, C, D, capital A, B, C, D, and some Roman numbers 1, 2, 3, 4, and equations on the right hand column. What we have to do is we have to match them with each other. And once you have figured out the correct combination, you can pick the correct option from the ones given below. So I'll read this out. The four names of the equations are the Fourier bio equation, the Poisson equation, the Laplace equation, and diffusion equation, and different mathematical fonts are given on the right hand side. So you have to mix and match and find out the correct combination.
Hello, sir.
Yeah.
Sir, I have a questions that the Stokes equations and the Euler equation, right? So the difference between them. So I want to know, sir. Means, in Stokes equation, what we do, and in Euler's equation, what we do.
Okay, so
Right? Which term we neglect, and in Stokes equations and in Euler equations, which term we neglect, right?
okay, so in Euler's equation, we ignore the viscous term, that is dou u dou x. Sorry, the second derivative of u, that we ignore, because the idea here is that the viscosity is low. The Reynolds number being very high, what does that mean? That the so Reynolds number is basically the inertial force by the viscous force, right? And Reynolds number being very high means inertial forces are much higher than viscous forces. So that's why we can ignore the viscous forces from the problem. And equation wise, we remove the viscous term from there. And that approximation is known as Euler's equation. So this is the Euler's equation. And in the Stokes equation, the Reynolds number is very, very low, which means the inertial forces are very low compared to the viscous forces. So one good example would be, let's say, honey flowing on a table or something like that. So honey, as we know, is a very dense, very viscous fluid, and it moves very slowly, or a case where it is moving slowly. So there the inertial forces are very low and the viscous forces are very high. So in that case, we can ignore these two terms, the inertial term and the temporal term, and only keep the viscous term in place. So that would greatly simplify our Navier-Stokes equation.
Okay, sir. Get it. All right.
Okay, thank you for clarifying. And so we'll go back to question number 8 now. It's a match the following type of question. So you have to match the two columns to each other and find out the correct combination. So you already started to get some answers here. Most of them are in favor of option C as of now. So let's see. So take your time, no need to rush to correctly match each of these terms to one another and find out the correct combination. If you have any questions, please feel free to ask. Okay, so let's go through each of them one by one. So option A, if the I'll remove this. So option A, Fourier bioequation. Okay, let's start from the other end. Let's say we start from D. the diffusion equation. What is diffusion equation among these three cases, or these four cases, sorry? Guys, don't feel shy, come on. Which one of these four is the diffusion equation? 1, 2, 3, or 4? It is 3, right?
Sir, third one is the diffusion equation.
Third one, right? Yeah.
Yes.
And which one is the Laplace equation?
First one, sir.
Correct. So anything which is a double gradient of something equal to 0, this is the Laplace equation. And if the double gradient of this is equal to, or if this is equal to some constant c, then what is this known as?
Poisson equation.
Quasi equation, correct. So this one, the option 2 would be Quasi equation. So that leaves us with option A being 4, the Fourier bio equation. This is basically, the unsteady cooling problem, unsteady cooling of a solid block. This is known as the Fourier bio equation. If we non-dimensionalize this, we get something known as the Fourier number and the Biot number as well. Anyway, so these things we learn in heat transfer, but for now we are just interested in the equations, and these are all related to different situations of heat flow. Basically, uh, uh, in the absence of any heat source, if you're trying to solve for conduction alone in a solid, then it would be a Laplace equation, that is option 1. In presence of a heat source, it becomes a Poisson equation. And in case we want to study an unsteady version of it, then it becomes the diffusion equation. Right? So this combination is A4 B2 C3 sorry, what did I do? C1 sorry, B2 C1 sorry, it could be C1 and D3. Which of these options match with it? 4, 2, and 3, that is C. So most of you in the chat box had selected C, and all of you are correct. Good. So let's have a look at the solution. It confirms that, yeah. So option C is the correct one. Any questions on this? Okay, if not, we will move along. We will move to the last but one question of this session, that is the 9th question today. So, what are boundary conditions in CFD simulations? Is it option A, information about the fluid flow at the edges of the computational domain? Option B, information about fluid properties such as density or viscosity or something like that? Is it option C, information about the fluid flow at the starting time? Or is it option D, all of the above? That is A, B, and C, all of the above. We have very aggressive answering in the chat box. It's a divided crowd. Someone has selected A, Many of them have selected option D, all of the above. Read the options carefully before picking your answer. So what are boundary conditions in CFD? Is it information about the fluid flow at the edges of the computational domain? Is it information about fluid properties? Or information about the fluid flow at the starting time? Or all of the above? Okay, it's a mixed crowd. We have someone answering C as well. Nice. B is also into the mix. So it's a perfectly split crowd. D again, that is saying all of the above. That is all A, B, C are correct. Right? Good. Now let's have a look at the solution. It is only option A that is correct. So boundary condition in a CFD problem, let's say if this is the origin and I have X and Y in these two regions. So these faces, I can call them X equal to 0, X equal to L, Y equal to 0, and let's say Y equal to H. So the information of fluid flow only at the boundaries is known as the boundary condition. Only at the edges of the computational domain. Now, what are the other things? Like information of fluid properties is not boundary condition. It is just, fluid properties. Information about the flow at the starting time. This has a particular name. Can anyone tell me what is the name of this? Yeah, correct. So it is known as the initial conditions. So in order to set up any CFD problem, you need two things. One is initial conditions and the other is the boundary conditions. Both have to be specified. So initial conditions will be specified at time t equal to 0, wherever you are starting the simulation from. And boundary condition is at all times what is the condition at the boundary. That is, for this case, for this example, it would be the values at x equal to 0, y equal to 0, x equal to L, and y equal to H. At these locations, what is the value of u or v, something like that. When I specify that, I am specifying the boundary conditions. And when I'm specifying what could be u over the entire domain at t equal to 0, then I'm specifying the initial conditions. Understood? So I can understand that the crowd was a bit confused regarding this question since there was such a mixed response. I hope this clears things up, right? Everyone got it, right? Why only option A would be the correct answer? If you have any doubts, you can ask. Okay, good. So now we will come to the last question of today's session. After this, we are done. Okay. So this is again a match the following type of question in which we have types of boundary conditions and their mathematical form. So these are the types on the left hand side and mathematical forms or expressions on the right hand side. You have to again mix and match to find the correct combination. And there are 4 combinations given in the options below. You have to pick from that. Okay, once again, very quick responses. Option B, option B, option C, again option B. See, you need to read this carefully and figure out the correct combination. Okay, don't rush. There is no hurry. We can do this in a calm and collected manner. We will discuss how to do this. So we have mixed responses between option B and C mostly. So let's try to go through each of them. So the first one is Dirichlet condition. So in Dirichlet condition, what we do is we specify the value of whatever physical quantity that we're interested in. What would be the mathematical form of it? We're specifying the value of whatever. So in our case, it is y that we are solving for. So y equal to f is the way in which Dirichlet condition is specified. So in a fluid flow case, you can imagine, I'll give you an example. So let's say I have flow through a pipe like this, and at the boundary, that is at y equal to 0, I'll tell that the velocity there should also be equal to 0 due to no slip boundary condition. Here what I am doing is I am specifying the value. Here you can compare, right? U equal to 0 with y equal to f. That is the Dirichlet condition where we are specifying the value exactly. Similarly, it's not that it has to be a constant. It can be something else as well. Like let's say for the inlet, we can say that U follows a parabolic profile like this. In that case also we are mentioning the value. It can be non-uniform, but we are mentioning the value nonetheless. So this also comes under Dirichlet condition. Okay. Now what about the second one, the Neumann condition? In this case, we specify the gradient of whatever quantity that we are interested in. So once again, one example of this would be a wall with a constant heat flux, constant Q, right? Q equal to C, let's say. Now we know that Q, that is heat flow rate, is basically it depends on K dou T dou Y, and this being equal to some constant can be converted to dou T dou Y being equal to something else, some other constant. So when we are specifying the gradient, the form it takes is basically dy dx is equal to f, where instead of specifying y, we are specifying the gradient of y. So dou y dou f, that is this one, A. So let's match things. Dirichlet is this one, Neumann is this one. Okay. Now come some interesting things. So Robin boundary condition, which is also known as mixed boundary condition. So in Robin boundary condition, we specify both the value and the gradient. So both y equal to f and dou y dou x equal to f is mentioned. So Robin would be option D, and it leaves us Cauchy equation with this one. Cauchy basically means a combination of both values and gradients is mentioned. So this is Cauchy's equation. So it should be 1b 2a and 3d 4c. So option D should be correct. Let's have a look at the solution. What? Sorry. It says 3C4D, so I must have 3C and 4D. Okay, sorry. So Robin boundary condition is this one, where okay, so yeah, sorry, my mistake. So mixed boundary condition means we employ uh, an equation which involves both the values and the uh, gradients, which is specified by some other value. So Robin boundary condition. So one example of Robin boundary condition is happens in natural convection, where let's say on the boundary we mention, let's say, the temperature as well as the uh, heat flux through it. The heat flux basically is a function of the temperature. So in case of convection, what happens is something like this. So this flux Q, let me write this. So the flux Q is a function of the temperature itself. So the heat flux is equal to the convective heat transfer coefficient into H into T minus T infinity, which could be some temperature in the ambient. And this Q prime, Q double prime, can be written as K dou T dou X equal to H T minus T infinity. So from this, can you see that this is an equation which has both the gradient as well as the value at that point. So this is a Robin boundary condition, which is a mixture of both. And Cauchy is a combination, like you specify both the value as well as the gradient separately. At this moment, I can't think of any example of a Cauchy type equation, but yeah, so in case there is a physical problem where you have to specify both, that is a Cauchy type boundary condition. So 4 would be D. Sorry for messing it up earlier. So it should be 1B, 2A, 3C, 4D. That is option B, as we can see in the correct option shown here. Okay, so any questions from anyone? Do we have something in the chat box? No. Okay, so if there are no questions from your side, that ends the uh, ends today's session over here. So it's been a great one. You've all been very enthusiastic about participating in each and every question. That's good. Like you have to keep this up throughout the entire uh, duration of the course. So we will meet again every Tuesday from 6 to 8 p.m. So every Tuesday from 6 to 8 p.m. we will meet within this session, and this would be the Google Meet link which we will be using every time. So you can use this link to join the course every day. And so that's it. So I'll stop recording now, and I'll ask, request some of you to stay even after I stop recording. Okay.